Hello there, and welcome to the greatest common factor. So in this video, I'm going to show you how to find the greatest common factor of two numbers. I'm going to show you two methods. One is basically just listing, and the second one uses something called a factor tree. Now, some of you may have never done a factor tree before, so I'm going to show an example of one. So why do we do factor trees? We do factor trees because every number is unique, just like every person is unique. So every number has a personal DNA, and we can see the DNA, the essence of every number, every integer, if we find the prime factorization of that number. And if that's a fancy word that you've never heard of before, that's okay, because once you see what I do, you'll know what I mean. So we're going to find the DNA of the number 24, and we're going to find the DNA of this number by factoring 24 in a series of steps. So the first step is just to think of any two numbers that multiply to 24. And the first one that comes to mind is, first pair that comes to mind is 2 and 12. And since 2 is prime, I stop this branch of the tree there, and I continue with 12. And the first thing that comes to mind is 2 and 6. This branch ends because 2 is prime again, and I continue two more branches from 6, 2 and 3. And I've reached the end of the last two branches because 2 and 3 are both prime. So I don't factor prime numbers since their factors are only 1 and itself. Okay, so that means the DNA of 24, which I'll write up here, the DNA of 24 is 2 times 2 times 2 times 3. This is the prime factorization of 24. This is the DNA of 24. Okay, so what does this have to do with finding greatest common factor? Well, if I have two numbers, A and B, and I want to find the GCF of those two numbers, A and B, one thing I can do is prime factorize A and B. And let's assume that I've finished prime factorizing them, and I get triangle times circle for A and triangle times square for B. The GCF of A and B is going to be identical to the common, whatever A and B have in common. Now this is different from how humans, the nature of human beings, because we get DNA from our mom and our dad, and then we become like a mix of those two sets of DNA from our mom and dad. But a GCF is a clone. It's a clone of the common DNA from A and B. It's an exact copy. So if the prime factorization of A is triangle and circle, and the factorization of B is triangle square, guess what? The GCF of A and B is triangle. It is the exact same triangle that exists in A and B. So let's do an example here. Let's find the factorization of 6 and 10. Okay, this is a simple example that you could probably do in your head if you've ever found GCF before, but I want to show you that the factor tree does work. So I prime factorize 6 and 10. 6 is 2 times 3. 10 is 2 times 5. So the GCF of 6 and 10 is 2, because it will be an exact copy of what 6 and 10 have in common. Now you might think, I could have just done that in my head. Why do I need a factor tree to tell me this? Well, it's true. You probably don't need a factor tree to find the GCF of 6 and 10, but you might need it if the numbers are not so small. So let's take a pair of medium numbers like 72 and 60. Now the GCF may not jump out at you when you see 72 and 60, so you could use the listing method, which is what some people do. So they might list the factors of 72 from least to greatest. So 1, 2, 3, 4, etc. And 60. 1, 2, 3, 4, 5, 6, etc. And I guess 5 doesn't go into 72, but 6 does. So maybe you might think, they both have a 6, so maybe 6 is the GCF. But you're not sure until you list all the factors of 72 and 60. So there's a bit of uncertainty in the listing method. Now, let's compare that to the factor tree method. So I start with 72. I go 2 and 36. I keep going. I go 2 and 18. And then 2 and 9. And then finally 3 and 3 branch off from the 9. Okay, now I go with 60. I'll start with 2 and 30. And then 2 and 15. And then 3 and 5. And I will see that both 72 and 60 contain a pair of 2's and a 3. So my GCF isn't 6, it's actually 12. And I'm 100% certain it's 12 because I can see the DNA here, and I can see that at most 72 and 60 share 2 2's and a 3. So there's a certainty in the factor tree method that you don't have in the listing method until you list all the individual factors of each number, which can work. I mean, it will work every time, but it's not the most efficient method, because if these two numbers are larger, the GCFs might not show up until the very end of the list. To support my point, let's try another pair. We're going to go with 168 and 120. Okay, so 168 is even, so I'll use 2 again. That's 84, 2 and 42, 2 and 21, 3 and 7. Now 120, 2 and 60, 2 and 30, 2 and 15, 3 and 5. And I see that there are 3 2's and a 3 in each of these factorizations. And so the GCF of 168 and 120 is 24, which is the number that we started off the lesson with, 24. And so there you have it. That's how to find the GCF using factor trees. Thanks for watching K109, and we'll see you later. Take care.